In this math counts preparation lesson, we are going to be talking about Diophantine equations. Now, before I actually explain what a Diophantine equation is, you don't really need to know any much prerequisites in this lesson, but watch the previous number theory videos. So the previous number theory videos on number theory, divisibility rules, you're going to need those for today. Now, when people hear Diophantine equations, they think algebra. But this isn't algebra. Diophantine equations are number theory. Now let's see how that's number theory. Chloe charged for admission to a play for 3 different nights. Each night a different number of people were in attendance. But remarkably, Chloe collected $541 each night. If the admission charges for each child and each adult, let's pair a child with the 9 and the adult with the 17, respectively, how many people in total came to the 3 showings? So basically, each night there's kids and there's adults attending. Alright, for each child it costs $9, for each adult it costs $17, and for each night, for one night, it costs $541. Of course, here's what we have. We can build an equation. 9 will let C be the number of children, plus 17A is the number of adults, and this is equal to $541. This is our equation, the first part of the problem. Now we have an equation, we have 2 variables, and there's nothing else. Now we could try to build a system, but we don't know any other information. And 3 different nights. We can't do much here. We have multiple solutions for this equation over here, this Diophantine equation. This is a Diophantine equation. Now let's take a look over here. What are our solutions going to look like? Our solutions have to be integers because the C and the A represent people, and you can't have a fraction of a person. So Diophantine equations are basically integer equations. We seek integer solutions, right? So those are Diophantine equations. Now there are certain techniques to solve these equations, and that's what we're going to be doing in today's video. We're going to be solving the Diophantine equation. Now, solving an equation is easy, but solving a Diophantine equation is a whole new problem. So basically, we've turned all of these words into this equation. So this is just a way of saying this. So we have 9c plus 17a equals 541. Now we could just guess and check, but guessing and checking works in number theory, not with Diophantine equations. So we're going to have to do something a little more smart. Now, how are we going to find values of C or A? Because obviously, Diophantine equations have multiple solutions. Obviously, this has multiple solutions. It has 3 different solutions because we're looking for all possible values of C and A, adding them up, and then adding every single sum of these pairs of solutions. That's what we're doing here. We're trying to find C and A, right? And then we take C and we take A, and that's what we're trying to find. So we're essentially trying to find all solutions to this Diophantine equations. And this Diophantine equation has only integer solutions. Now let's play around a little bit. Let's see if C is 0. If C is 0, we have 9 times 0 is 0, and we're left with 17a equals 541. But 541 can't be a multiple of 17, since if we just try to imagine we're dividing, 17 times 3 is 51. And that's going to give a 3 when I subtract off the 51 from the 54. And of course, 17 times what equals 31? Well, 31 is not divisible by 17. So C can't be 0. What if A is 0? Let's set A equal to 0. If A is 0, we have 9C equals 541. Now you know your divisibility rules for 9. The sum of the digits must be divisible by 9. 5 plus 4 is 9. We have one extra 1, that's a 10. So essentially, and let's see if they can be equal, our last case. Well, if they're equal, we have 17 plus 9, that's 26. Right, and it's 26. x, let's say 26a or whatever, equals 541. And 26 isn't, because if you multiply 26 times 2, we'll get 2 unit digits. And then 2 times 2 is 4, carry a 1, you get 52. And it'll look 21 when you subtract off everything, and that's 2 less than 26. So they can't be equal, and they can't be equal to 0. So we need to write down some rules. Right? A can't be 0, and C can't be 0. That's all we know. So we know they have to be natural numbers. Well, that doesn't really help us because we still have tons of things to check. There's not a lot of solutions. There's only 3 solutions to this problem. Or not the problem, the equation. There's 3 solutions to this Diophantine equation. Once we've solved this Diophantine equation, we're basically done with the problem. So let's go ahead and figure out ways to solve the Diaphantine equation. One way we could start is by taking away multiples of 9. Well, if we take away a multiple of 9 from 541, we should keep taking away multiples of 9 until we hit a multiple of 17. And when we hit that multiple of 17, well, that number is a multiple of 17. And the distance from that number to 541 has to be a multiple of 9, since we're taking multiples of 9 away. Now that's not pretty easy because, well, we have to check for multiples of 17, and checking for multiples of 17 is hard. Let's take away multiples of 17. If we take away a multiple of 17 from 541, well, all we need to do is find a multiple of 9. Once we find a multiple of 9, we need to find the distance from that multiple of 9 to 541. The difference is going to be the distance. The difference has to be a multiple of 17, and then we can just find C and A. So I think it's easier for us to tackle the problem by taking away multiples of 17, because then multiples of 9 are easy to find, as some of the digits has to be divisible by 9, and then hopefully we can find a pattern, do all sorts of good stuff. So let's just start off by taking away a multiples of 17. Let's just take away one multiple of 17. Let's start off with just 541 minus 17 and see what happens. Look at the sum of the digits. We want a multiple of 9, so we look at the sum of the digits, because that's a divisibility rule for 9, right? Now I'm going to go ahead and do our subtraction. We get a 4 over here, get a 3 over here, get a 2, get a 524. Sum of the digits, 5 plus 2 is 7, 7 plus 4 is 11. This seems interesting. Let's take away another multiple of 17. Let's take away 17 times 2 is 34. Let's take away that. The unit digit procedure is the same, but now we have this. And by the way, this is 11 minus 4, so this should be a 7. And this is obviously just a 5. Now check this out. This is 5 plus 2 is 7, 10 plus 4 is 11, 5 plus 7 is 12. We might have a pattern on our hands. Let's go ahead and see 17 times 3 to make sure we have a pattern. 17 times 3, what's that? That's just 51. 1 minus 1 is 0. Then we have a 14 here. 5 plus 9 is 14. And then this turns into a 4. There's a 0 here. 490. We seem to have a pattern. 5 plus 2 is 7. 7 plus 4 is 11. That's the first multiple of 17. 5 plus 7 is 12. Second multiple of 17. And 4 plus 9 is 13. Third multiple of 17. We have a pattern going on here. Now, what's the rule for 9? The divisibility rule for 9 states that if a number is divisible by 9, the sum of its digits has to sum to a multiple of 9. Now, if it sums to a multiple of 9, what's a multiple of 9 that is greater than 11? Well, 18. 18's in the teens. It's pretty close by. We can just find that. Now, if we start from this 17, we go up to for sum of the digits. So the sum of the digits, this one has to be, so we already know it's 11, 12, 13, on and on and on. So if the sum of this digits is 11, 12, and 13, we can just find what to subtract off from this 541 to obtain a multiple of 9. Let's just do that, okay? 11, 12, right? 11, 12, 13, 14, 15, 16, 17, 18. That's 8 multiples of, that's 17 times 8. And 17 times 8, well, let's see if we have that. So, 17 times 8, all we need to do is compute that. Now, 17 times 8 is an easy product to compute. 8 times 7 is 56. 8 plus 5 is 13. It's 136. Now let's take a look. Let's just say we have 541 minus this 136. Interesting number. This turns into a 3. And this is just 405. But take a look at this. The sum of the digits is not 18. But who cares? It's 9. It's a multiple of 9. We've found one of the numbers we're looking for. Now, we can go ahead and we can find C. All we need to do is just divide this out. So we can find C by doing 9. We can just have this division. Right? All we need to do is do this division and we're done. 45. So I can go ahead and stick a value of C in. And now I need to find A to complete one solution to this Diophantine equation. And the other solution, let's just check how we're going to find that. We have this 405 over here. We have this 136 over here. Now when I take this 541 and I subtract off this 405, I'm gonna get 136. This distance is 136. That means if I start with 45 times 9 and add on 17 times 8, I get 541. 17 times 8 is this 136 lying in there, so we know A has to be 8. Just like that, we figured out one solution. We can move on to the next solution. We can erase all of this mess over here. We know a pattern. Okay, so we're at 405. Let's see what we have to do here. Because instead of here, we want to check if our pattern's working. Because patterns can change sometimes. Don't always assume your pattern works all the time. So we're at 405. Right? Right, we're at 405. Let's subtract 17. It's a multiple of 17. See what we get. This is 8. This is 10, but then we carry that 9, 8, and then we have a 3 over here. 388. Let's check out the sum of the digits. 8 plus 8 is 16. 16 plus 3 is 19. That makes sense since before that it's supposed to be 18, but it was actually 9. Right? We assumed it's going to be 18 since the pattern would turn out to be 9. So we have a 19. It makes sense. Let's see what else we get. Let's take 388. And let's subtract off a 17. Subtract off a 17. 1, 9, 3. We get this. 391. Well, what do we have here? We have 391. When we take away 17, we start over here, we take away 17, something is going on. Because 8 minus 7 is 1. 8 minus 1 will be messed up on the subtraction. Always look for errors because they can mess things up. 8 minus 1, that's 7. That's not 9. Now we have 371. Alright, so 3 plus 7 is 10. 10 plus 1 is 11. Something interesting is going on. So we're back to 11. Let's see what happens if I take away another from 38. Interesting. 8 minus 4 is 4. 5. 3. 5 plus 4 is 9. 9 plus 3 is 12. Oh. Well, we're back to this. We're back to 11, 12. And this honestly makes sense since units, like, let's keep going. Let's just take away another one, right? Just to get a feel for things. 388, we can subtract off 17 times 2 is 34, 17 times 3 is 51. And that's just the same as taking away 17 from 354. 8 minus 1 is 7. 3, and this is 3. 3 plus 3 is 6. 6 plus 7 is 13. We're back to the same pattern, so we can just forget about this. Since we care about this pattern, right? This is the pattern we seek. This 11, 12, 13, sum of the units, sum of the digits. So now we can use this same strategy. We just take away the respective multiple of 17. All right, let's go ahead and do that. 11, 12, 13, 14, 15, 16, 17, 18. That's 17 times 8. We already know that's 136. So we can just do 388 minus 136. 8 minus 6 is 2. This is 5. This is 2. 252. We have a multiple of 9. 2 plus 5 is 7. 7 plus 2 is a 9. So we have this 9 over here, this multiple of 9. Now let's check it out. Let's just find another value of C. Let's just do some division. Figure stuff out. We know that 9 times 2 is 18. Right, and then we have 7, 2, and this is just 0. So we have 28 is another value of C. And then we just need to find the respective value of A, and we will be good to go. Now let's see what happens. Let's just start with a 541. Stick with a 252. Let's see what happens. Since that's what we're doing here. We found the value of C. 28 times 9, that's 252. Now we should subtract it off from this and find this A. So this distance must be a multiple of 17. So let's see what happens. This is turned into 13, 8, 4, 289. That's a really nice number since 289, I know that's a perfect square. I know my perfect square is up to around 17, of course, or 17 or 18. It helps know your perfect square is up to 20. So I know 289 is a perfect square. I also know it has to be a multiple of 17, so what do I know now? This is 17 squared. I already know this is 17 squared. Let's just plug it in. So we know this A has to be a 17 because I know my perfect squares. Now we can go ahead and repeat this process. I'm going to leave this up here to make things a little bit more convenient for us, but now we know what's going to happen next. Now let's do the same thing. Where did we leave off? We left off at 252. All right, let's start at 252. All right, and when I'm starting off at my 252, I'm going to start with my 252. And when I start off with this 252, we're going to take away these multiples of 17. And when I take away these multiples of 17, I should get the respective values that I want. Right? We always want to relate everything that we want to what we're trying to do. So let's just do this, right? Now let's just start. So we can go ahead and start with a 252, and then we can just take away multiples like we usually do. Right, so I can start with this 252, like we did on the previous one, 252. Now let's take away just a multiple of 17, see what we get. Now this will turn to a 12, get a 5 over here, get a 3 over here, And then we'll over here, we carried that, and we're basically done. 235. Let's see, 2 plus 3 is 5, 5 plus 5 is 10. Okay, that's odd. We have, well, it's not odd, it's even, but it's like, it's awkward that we got that. Let's try taking away another. Let's hope we get the same pattern, and then things will just be fine. Get a 12 over here, get an 8 out over here. Yes. It's working. Okay, so we know it's working. But this time stuff is a little bit more interesting. This is starting at 10. We're trying to get to 18. So let's see if this actually is going to work. And if not, we're going to correct. We don't know yet. This is a part of doing problems like in a number theory, is to always check. Guessing and checking is good. Like a part of your problem can be guessing and checking. So let's start with this 10. Let's do this. 10, 11, 12, 13, 14, 15, 16, 17, 18. This time we have 17 times 9. So I'm going to go ahead. Well, 17 times 9. Let's see what that is. I'm going to write it vertically so it's a little bit easier to compute. So we have 153. Now let's see, do the subtraction. 252 minus this 153. Now, the most helpful part of this problem is this increasing sum of the digits. Always note that. This is a 153. This is a 12. Has to be a 9. Now this gets demoted to 4 and gets that. We get a 9 out over here. Get a 99. A 99 is a multiple of 3. This will turn out to be great. Now, since it's a multiple of 9. It's a multiple of 9. 9 times 11 is 99, so we already know A off the top of our C off the top of our head, because we know 9 times 11 is 99. 9C equals 99. C equals 11. We're literally 3/4 of the way done. Just need to find the last value of A, and we're almost done. We're back on the last part of the problem. We have a 289 we have a 99 out here. Let's subtract that 99 off from this 541, and again, this should give us a multiple of 17. Now I take this out, I'm going to get a 2. I'm going to get a 2 over here, and then over here I have an 11. It should be a 3. Then it should turn to a 13. Since we had to carry, this should turn to a 442. Let's try to add that, make sure it all adds up, since subtraction can get a little messy sometimes. 2 plus 9 is 11, 13, 14. Okay, adds up. So 442. Let's see if that is actually a multiple of 17. Seems odd. 17 times 2 is 34. And then we're left with this difference of 10, 102. Now I know that 7 times 6 is 42, so I know the units digit 17 times 6. I'm going to test out this 17 times 6. And sure enough, that's what I'm going to get. 6 4 is 10. I have this 26 lying out here. We know the value of A, and this is turning out to be great. We know this is 26, so we can just plug that in right here. And that's it, right? So this is day 1. If you forgot what the problem was, let's go back to the problem. We're having a play each night. So this is day 1, this is day 2, and let's let this one be day 3. Right? Doesn't matter what order they're in. And then we want the sum. We want the sum, like how many people in total came to the 3 showings. So how we're going to do this is we're going to find how many people came in total to the first showing, second, and third, and just add them all up. So we're going to start with the sum of this. 45 plus 8. Well, 45 plus 8, what's that going to be? Well, that's just 53. right? And I have 28 plus 17. Now 28 plus 17, that's an easy sum to compute. We have 5 in the units digits, and 2 plus 1 is 3. And then I carry off the 1, so I add a 4, I get a 45, right? That's what we get. And then I have an 11 and a 26. Well, 6 plus 1 is 7 from the units digits, and 2 plus 1 is 3. So that's an easy sum to compute. The only one we're skeptical about is 28 and 17, so it doesn't hurt to check to see if we're right. Okay, we're right, 45. And now we can just take the sum of all of this. And then once we take the sum, we will be done. Now I'm just going to do this with some intuition. 7 plus 5 is 12. 12 plus 3 is 12, 13, 14, 15. So I'm going to have 5 out here. And then I'm going to place a 1 up top. 4 plus 3 is 7. 7 plus 5 is 12. 12 plus 1 is 13. So after adding all these up, we have our solutions right here. But more importantly, the sum is 135. And this is the total amount of people that came to the 3 showings. Obviously, in the real competition, this would be much faster than guessing and checking, because all we needed to do was recognize this useful pattern. The sum of the digits pattern, know your divisibility, and Diophantine equations are made easier. We turned this hard number theory problem into some basic computation.